Shashla. Good afternoon, everyone. Welcome to this installment of the Industrial Seminar Series for 2024. Today, we've got two excellent speakers with us from Sasol, the global chemical and energy company that was founded in South Africa. We really appreciate their participation in the program today. We're looking forward to what they have to tell us. I invite all of you to pose some questions in the chat bot to be answered during the scheduled Q&A session after the talks. Without any further ado, I'd like to introduce first our first speaker, who is Dr. Braam van Dykshared. He is a senior manager for process engineering and modeling with a wealth of experience that he'd like to share with us today. And his talk for the seminar today is entitled "A Day in the Life of an Industrial Research Engineer." I'd like to now invite Braam to join us and take over with the talk. Please give him your kind attention during this time. Thank you, Braam.
All right, thank you very much. Let me, can you see these slides? And I can continue. All right. All right, so a day in the life.
Not showing.
Oh, it was sharing a second ago. Let me try that again. There we go. Better.
Okay.
Okay, so a day in the life of an industrial research engineer. It's a bit of a broad topic. So maybe let's start day in the life of who again? So I'm Braam van Dykshared, Senior Manager for Process Engineering and Modeling, which is in Sasol's R&I, Research and Innovation Division, previously known as Research and Technology, previously known as Research and Development, soon to be known as Research and Technology again, I understand, but anyway, it's research. I studied a long time ago in a galaxy far away in the University of Stellenbosch. I guess I got my PhD by the time most of you weren't yet born. So yeah, I'm not quite a boomer, but I'm next best thing, a Gen Xer. And my career in Sasol is now 22 years. All of that in the research department. Started off in separation technology, then a short stint in gasification, followed by a rather long one in Fischer-Tropsch. Currently covering Fischer-Tropsch, refineries, chemicals, and advanced process modeling, including a little bit as a sideline machine learning. So I've always jokingly referred to myself as a specialist generalist. And maybe pause there for a second. You guys are on the start of your careers. Some free advice from a guy who's been around the block is don't specialize too early. What you'll find is the innovation happens on the interfaces between areas. And I can tell you we've made some nice progress bringing knowledge from Fischer-Tropsch into the refinery area. Not the chemistry necessarily, but the ways of doing things are different. And then taking them back into the FT area and vice versa of all the other areas. So you can be your own multidisciplinary team if you have a broad enough experience. Okay, so let's have a look at what would you do if you were working in industrial R&D. So maybe let's start a bit wider. What does a chemical engineer do? So I made the mistake of asking the internet, and maybe my mistake was asking Bing and not Google, but I did ask Bing. I just put in chemical engineer and looked at the images. And this is what we get. That's a lot of lab coats. So if this is the information you're getting, then you're going to definitely have a bit of a culture shock when you do arrive in industry, because you won't see many lab coats, definitely not in the engineering side. And I understand these are all, research departments at universities. But let's maybe not take this as our starting point of what a research chemical engineer does in industry. Okay, so this is much closer to reality. This is what most of our engineers are going to look like. We're walking around in overalls and hard hats on the plant, even in the R&D division. I'm a manager. I get to sit in my office all day, but I still get out in my overalls every so often when we're piloting, when we're troubleshooting, etc. Right? But here's also a photo of what one of my engineers refers to as the scariest thing on a plant, and that is an engineer of a clipboard. So keep that in mind if you're ever walking around on the plants. All right, so process engineer, chemical engineer, call it what you want to. It is a very, very wide field. And if I just look at the very broad categories, the bulk of the engineers work in production and technical support. And these are the guys who, I say, run the plants. They're not the operators, they're not the technologists, right? They are always engineers on the plant as well, and they are accountable for making sure the plant will run to spec. When things break, they get fixed expeditiously. They troubleshoot, they optimize continuously, right? And then there's another, maybe a slightly smaller department, which is the design and project engineers. These are the guys who do the nuts and bolts design. They will size the pieces of kit. You need a heat exchanger, they will do the process design and then work with a mechanical engineer to do the mechanical design of that piece of kit. And they will then run the projects that, manufacture the pieces of equipment, install the pieces of equipment, integrate them with the rest of your plant, and then start it up and hand it over to the production team. And then there is a significantly smaller little tribe of research engineers. So research engineers are the guys who develop the technologies that we turn into new processes. So if we want to build a power to liquids plant, well, the first thing you need there is you need a Fischer-Tropsch technology. You need a reverse shift reactor. So you need that reverse shift technology, maybe electrically driven reactor rather than burning methane to heat up the reactor, for example, right? So these are the things that get developed by the research engineers. But it's not a piece of kit in isolation. It's a technology sitting inside a process. So the flow sheet that goes around that is developed by your research engineers. And then that gets handed to the design engineers to go turn that into a physical piece of kit on the plant. Once that plant is up and running, we don't walk away or go back into our ivory towers and do, well, it's R&T, so we rest and think, right? So R&I, rest in introspection. We actively support those plants because, especially when it's a new technology, a new process, the plant support engineers will not have experience. They will not have that in-depth understanding of the chemistry, of the physics of the process to be able to sort out all the issues. And maybe even 10 or 20 years later, there's always a turnaround of engineers on the plant. There's always one or two old guys and a lot of young guys, and they run into problems they haven't seen before, and when we go and help them sort it out. And then you must also understand there's even inside that small tribe of research engineers, two sub-tribes, right? There's academic and there's industrial research. So let's have just a quick detour into that. And, this is one person's view. It's not necessarily all-encompassing. But in academic research, it's a search, you do research to advance the fundamentals, to advance the engineering sciences, right? You develop new technologies, yes, but you're not limited to things that will have immediate industrial application. You can study new fields that may never see the light of day, or 20 years from now, may be the hot topic everybody wants to build. I guess you have to wait and find out. And then they also train up the next generation, right? We all got trained by academic research engineers. Industrial research is much more driven by immediate problems. Immediate, okay, is a bit of a relative term. For an operations support engineer, an immediate problem means I need to solve it in the next hour or there's going to be trouble. For an industrial research engineer, immediate means this is something we need maybe in a year or two, and it's going to take 18 months to build the thing. So we've got 6 months to a year to develop the technology to feed into that design. It's much more an application of the engineering fundamentals than it is advancing the engineering fundamentals. So if you want to think about this in terms of pure science versus applied science, I think that's probably a fair view, although it may upset a few of my colleagues. We're much more involved in developing and scaling up technology. So, academic would definitely also develop new technologies, as do we. But scaling up technologies is something which I think is much more on the industrial side, simply because we've got the toys to do that with. We'll have a look at that a bit later. And then a very, very large part of what we do is techno-economic valuations of technologies. Technologies we develop, we go through several stages of techno-economics. when we look at external technologies, the first thing you do is a techno-economic evaluation. And so what is a techno-economic evaluation? You look at the technology and will it work? First question, will it work in our environment? And if it does work, will it make money? All right, because companies are fundamentally in the business of turning a profit. And if a technology is going to make a loss, then you must not implement it, right? I still need the plant to run and pay my next salary, so I need the plant to be profitable. Now you can see that these branches have overlap, but they're also very complementary, right? If there isn't fundamental research in universities, there's very little for me to apply because we are not in the business of doing that fundamental research. We're in the business of finding applications for it in steel on the ground outside my window. Okay. So definitely complementary, although there can be a lot of overlap. And this is why Sasol tries to be very involved with universities and sponsoring research and making sure there's critical mass there as well, because it is fundamentally feeding into what we do. Okay, but this doesn't tell you what I do, so let's have a look. So broadly, okay, just keep in mind, it's a Sasol viewpoint. Your mileage may vary, as the old expression goes. If you go to a mine or a minerals company, or for that matter, another chemicals company, they may have a different view of how this works. But it is, I think I've tried to be as general and broad as possible here. So we are going to split what we do into business of today, which is the plant support, and business of tomorrow, which is the technology development. So let's start with business of today. The plant is there, it's running, right? There is a team of engineers who troubleshoot the plant, who optimize the plant. They know that plant, right? They've been there for, some of them, 20 years. They know that if you do X, Y happens. And if a problem has happened before, they will know that history. They will know what caused it. And it's a good place for them to start troubleshooting. It's from experience, right? In contrast to that, when we go and do plant support, I will never have the same level of experience with that piece of kit that the plant engineer does. But I have experience with 25 other plants that may have similar processes or relevant technologies. I have the ability to bring all of our research divisions, machinery to bear. We've got lots of scientists and labs and pilot plants. We can go and conduct experiments. Right? An experiment is not something you want to do on plant scale, because something can go wrong on plant scale, the implications are also much larger. So we go do the experiments in the lab, in the pilot plant. We run scenarios, we build advanced models, which is more something we get to spend time doing than the plant engineers do. And because we don't have the experience, we must approach every problem from a fundamentals first principles approach, right? We understand the fundamentals of mass transfer, of heat transfer, of reaction kinetics, of catalyst deactivation. And we bring a different toolbox to the problem than the plant support engineers typically have to their disposal. And so again, we don't go and help them because we're super smart. We go and help them because we bring a complementary set of skills. But, you know, without them, we'd also be maybe out at sea because we don't have the history, we don't have the in-depth understanding of the plant's intricate control loops, etc. So we work together to solve new and complex problems. If it's a simple problem, they don't need us. And if it's a recurring problem, they also don't need us. It's when the pawpaw hits the fan in new and interesting ways that we go and support them. And then we also learn out of the process, we improve our technology for the next time. So technology development is never a thing I do and then I build a plant and then I walk away from it. It is always an iterative learning process. So now we learn things by supporting the plant, and we use that when we do what we call business of tomorrow, right? Developing the next big thing. So maybe just a pause here and show you how we structure our department. Okay, so business of tomorrow is why R&T exists. It's why it's a corporate asset. We are meant to be focusing the majority of our time on building the technologies we need to bring Sasol to 2030, to 2040, to 2050, right? And to do that, we have teams that have specific specialization areas, but there's also huge overlap between them. Right? So we have 4 teams in engineering research. There's my team, process engineering and modeling. So the area we specialize in is going to be custom advanced models. Again, every engineer should be able to model. Every engineer should be able to build an Aspen simulation. But if you need an advanced custom reactor model or reaction kinetics, etc., that's what we have more experience in than the other teams. So that's the area we are accountable for maintaining the competency for. Then we have a small team sitting in Enschede in the Netherlands. Incidentally, one of my team members sits there and 2 of my team sits in Secunda, the rest are in Sasolburg. The team SHN, Sasol Holdings Netherlands, their focus area is much more on fundamentals. So they've got some what we call cold models. So it's a reactor model or a filter model or whatever model where you flow water and air and inert particles through in lieu of catalyst. So we can do low temperature, low pressure experiments in glass where you can see what's happening. There really is never a substitute for actually physically being able to see what's going on inside. That's the one thing that's always the issue of chemical engineering, right? When you can see the process, something has gone horribly sideways. When things are working, it's all just nice and boring. We like it that way. When it gets exciting, there's trouble. Okay, so it's nice to have the ability to see things in glassware. We've got a lot of glass distillation columns as well. They are really, really educational. Okay, and then they also organize and coordinate support for Sasol's plants in the North America and in Europe. We also have a plant in China. And of course, there is Oryx in Qatar, EGTL in Nigeria, and UzGTL, which is in Uzbekistan, but that support for those units get coordinated through our licensing team, but support for the Lake Charles units and the German and Italian plants that is coordinated through SHN for the rest of us. We all support, but somebody has to be the contact point. Then we have a reactor engineering team. So their focus is going to be on proprietary reactors, like our FT reactors, designing those. And catalyst, not developing the catalyst, that is our science teams, but scaling up the production of the catalyst, right? Our scientists would develop a catalyst recipe in the lab on gram basis, but we need to make that in tonnages. And scaling up that process to a plant making 1,000 tons of cat a year is what these guys specialize in. Just incidentally, Sasol, when it comes to making large volumes of cats, are definitely world leaders. The 2 catalyst plants we have in Secunda are each on a mass basis, individually the largest catalyst plants in the world. We go through a lot of catalysts in Secunda. Okay, this is just our FT cat. There's also about 50 other catalysts we buy in from other places for refinery and chemicals purposes. Then we have an environmental engineering and separation technology team. This used to be 2 separate teams. We merged them at some point because if in the bottom line is in environmental technology, there is a lot of separations in there, right? There's capturing the stuff before it goes into the air, whether you use adsorbents or you wash it down. It's the same technology the separations guys would use to purify products or purify feeds going into the reactor. So there's a lot of synergy there, and we just merged them into one team. Okay. All right, so those are the teams. So how do we go about doing our work? Well, when we're trying to develop a new technology, it all starts with a calculation, right? It all starts usually with a simulation in Aspen Plus, and maybe we need to develop a reactor model because there isn't the right one in Aspen. Aspen has got some very lightweight reactor models. So unless you have a specific stoichiometry with a fractional conversion, or you have already kinetics, and then you only have ideal reactors, plug float, CSTRs, anything in between, anything a bit more advanced, we have to build our own models. So that's usually where we have to start, but we've got a large library of them by now, so it doesn't take that much work. And then it's also our job to make sure you get all the right physical properties, right? I teach a little in-house course in Aspen Plus for our young engineers, and about the first thing I tell them, if you're not spending as much time sorting out the physical properties you are building the sim, then you're doing this wrong. It's not a computer game, right? The answers are as good as the inputs, and the bulk of your inputs are in your physical properties. So we do spend a lot of time making sure we get that right. Otherwise, you just get to the wrong answer fast. So we've done the calculations. And what do we do when we've done the calculations? We have to do techno-economics. And the first step in techno-economics is, what is this plant going to cost me? So we have to do a cost estimate. Now, you guys will do cost estimates in your final year design, absolutely. And what you may think is, well, there's going to be a department of specialists that does cost estimation, and you will be right. Except the cost estimators in Sasol only come into the game quite a bit further down the line. So when we already have finished a conceptual design of the plant, right, we're going to go into basic and detailed engineering is when the cost estimators come in line. So in the area where we play, when it's technology development and it's vague and lots of unknowns, they are not involved at all. And our R&D engineers do the cost estimates, what we call a level 5 or a level 4 cost estimate. So, you know, by the time when you have a capital number, but it can be double or half that. And this is a skill that we require all of our engineers to develop, and because a lot of this is judgment based. And if you work in industrial engineering research, this is something you're going to spend a lot of time doing, is figuring out how much things are going to cost to build. And then once you have the cost, the capex, the opex, the product prices, the feed prices, you can go do a detailed techno-economic analysis. You do a sensitivity study. Does this make sense? When does it? When does it not make sense? To understand what are the main technology risks and the cost drivers, so I can understand under which circumstances would it make sense to build this plant. And if those circumstances are a tiny corner up in the design space, then maybe it is not worth spending more of our resources on developing this technology. And it is important to decide early on that this is going to be a waste of time. You cannot work up 50 or 60 options to a detailed level and then pick one. You really need to start eliminating options very early on, and you have to be ruthless. So techno-economic analysis and learning when to let go of what was your pet favorite idea is an important skill in the job. And if we say there's value in this, then we go into the research phase. And then our scientists, I was joking with the manager of our FT research team that I took one of his photos, and he did say it's a flattering photo. So I'll leave that to you to decide. So then we start doing research, right? This is when we unleash the full might of our science department. But it's not scientists go and do and then they come back 6 months later. The engineers are part and parcel of this, because we need to tell them what we need to know, and they need to do that research. So you understand the chemistry. What are the reactions? What are the side reactions? What are the kinetics? What product specs would we need to meet for this product, and what impurities can we expect, and under which circumstances do they form or not form? What would be our catalyst lifetime? What causes the catalyst to deactivate? In the end, when we build a kinetic model, building the rate model is easy. Building the deactivation model is the hard part, right? But it is as important, because the rate model just tells you how big the reactor must be up front. It doesn't tell you how much catalyst you need, and the catalyst cost is going to drive your economics at the end of the day. And so we do, at the end of the research phase and continuously throughout, a techno-economic analysis again. And we take a look at those risks we identified in the previous stage when we were just evaluating the idea. Have we addressed them? Have we mitigated them? And what new risks have we identified? Until we have worked those risks down to a level where we believe, okay, we have a handle on this process, we understand what drives it, what will make it work, what will make it fail. And then we look at the economics. Is it worth going ahead? Yes or no? And again, you need to be ruthless in stopping projects, even if you think it's the world's coolest technology. If it isn't going to pay for itself, you cannot justify building it. And if it is going to work, then we move on into the next phase. And the next phase after research is scale up. And this is now, again, 100% an engineering activity. Okay. This is where we start piloting. So you've done your proof of concept work on lab scale. You've done your preliminary kinetics, etc. The next stage is to go look at pilot plants. And you can imagine this will cost you a couple of rands a day to run. Pilot plants can cost thousands to tens of thousands to hundreds of thousands of rands a day. Or bench scale reactors, factoring all costs, this is now chemicals and man hours or person hours needed to run them. Bench scale reactors can be like 50,000 rand a week. Pilot scale reactors are probably like 50,000 rand a day. Demonstration scale reactors, so we're talking about, we've got a big FT demonstration scale reactor outside here, which is 60 meters tall, 1 meter diameter. That can be easily 500,000 rand a day to operate, right? You don't go lightly into that level of demonstration. You work your way up through the sizes, the scales, so that you always have only specific things you want to answer. You don't want to just run the thing and see what happens. That you can do on this scale. And then when you feel you've now identified and mitigated all the risks, then you go to this scale and you identify new risks, because now you have different hydrodynamics. Mixing is different, heat loss is different. You find mechanical attrition of the catalyst, which was not an issue on bench scale, for example. You start looking at dynamics of the process. How do you start this up? What happens when you trip? What do I have to do to prevent damage to my catalyst during a trip? Do I have to immediately purge the thing of nitrogen? Do I have to quench, cool it? If it does damage the cat in a trip, how do I recover it? What are the main things I need to control? And then you work your way up to larger and larger scales until when you eventually build the full scale thing, you don't have surprises when you start it up, right? Chemical engineering is great when it's boring. You do not want excitement, because excitement usually means you missed something. And then you have an exciting startup and you become famous. And about the biggest fear anybody has in industry is becoming famous, because that means, management have questions for you you need to answer, and you may not have the answers for. Okay, so we do our due diligence. We work our way up through various scales until we get to the end. And at every stage, techno-economics, risk analysis. Have I mitigated the risks? Do I understand the risks? Have I worked them down to an acceptable level of risk? Techno-economics, is it worth going ahead? All right. And in the scale up, you discover chemistry that you didn't see at small scale, and then you go back to the lab and you reinvestigate it. And then you go back to piloting, and maybe you pilot at a slightly different set of conditions, and then you find something else again, and you recycle again. Many times until you finally have wrapped up your technology development. And when we feel we've now finished wrapping up our technology development, it's review time, right? This is like your final exam now. And we take it very much the same way. We have a team of independent technical experts, and the key words here are both independent and expert, right? So this would be a guy who is not on the project, but has 10, 20, 30 years experience in the field. There will usually be an engineer and a scientist, and they pull apart everything we've done. They look at all the questions we've asked, all the answers we think we've developed, and at the end of this review, they have to say whether or not they are satisfied that we have identified and addressed all of the technical risks. They also look at how we do the economic analysis, what assumptions we've made. Do they agree with the assumptions? If they question the assumption, we must, work with them to make sure they are satisfied, until when they are willing to sign off, then we take this technology package onto what we call a technology governance forum, where we asked for already for implementation, RFI status. Okay, this is also, I get a bit of a disease in the industry that we reuse the same abbreviations. So RFI can be a request for information, which is followed usually by a request for quotations, but it's also ready for implementation. So when a technology has ready for implementation status, it means we now offer this technology as an option to our capital projects. So say, for example, we've developed a new Fischer-Tropsch catalyst for GTL applications. The existing catalysts are, of course, there for the guys who designed the plant to use, but now we're also offering them our newer generation upgraded catalyst, and they consider that as well as an option. maybe they now immediately drop the old one, but usually we would do an economic assessment for both options, and then only under, when the new catalyst is clearly better for that specific application will be picked. Same for a new reactor design, etc. It's an option, but finally the choice goes with the owner of the capital project. So we offer them options, and then we stop. And then when the plant is under design, they may come back to us for inputs, questions during the design phase. When the plant's being started up, we would usually send people to support the startup, because again, we are now the technology experts. We are usually the licensors. And when the plant is up and running, then we also troubleshoot and monitor, especially on our proprietary technologies, and we support. Okay. So it's working your way up to your final exam. And then RFI status basically says, congratulations, you have passed. But it's also a bit like having a kid. You have to keep on supporting them for quite a few years later still. All right. So that's the process of developing a technology. But before you can develop a technology, you have to have some ideas of what it is you want to do, right? So we must first understand what are the options, understand the problem, and propose some technical solutions. So let's take an example. And if you guys want to do this interactively, that would be fantastic. But otherwise, you get to listen to me drone on for a few more minutes. Let's say we have a specific business problem, which is your company, wherever you work. Almost every company on the planet has now made a commitment to a greenhouse gas reduction. I was just reading last week that Air New Zealand are now walking back their commitments for a 30% or 29. It was such an arbitrary number, a 29% reduction by 2030. And they're probably going to settle for what the aviation industry has proposed, which is a 5 to 7% reduction. Okay, but your company is now committed to X% by 2030, because that seems to be the date everybody is committing towards greenhouse gas reductions. The trick is, of course, how do you do this while maintaining profitable? And this is a big problem, right? Technically, reducing greenhouse gas emissions is not a big problem. I can probably, give you 20 technologies that technically will work, but you can't afford any of them. And therein lies the rub. That is the whole problem you need to solve, is how do you make this economically viable? I mean, technically, if I had green hydrogen and I captured CO2, I could just run it through a reverse shift reaction. That's not new chemistry. It's not new engineering. We've been doing reverse shift for a century. But if you go look at electrolyzers and other sources of green hydrogen, you're looking at about $6 a kilogram. If you're looking at direct air capture technologies to capture CO2 out of the atmosphere, that's at least $1 a kilo. So now you want to make petrol out of that, but your starting materials is already 20-something rand per liter, and you haven't even built a plant yet. So it's not a small problem to solve. Aviation, especially, about 25% of their cost is fuel. They would not want to pay multiples of that for a green fuel. On the other hand, making a green fuel at this point is also not going to cost only a few percent more. So there's a big gap between what we can do and what we need to do. And it is going to be industrial research and academic research job to bridge that gap. So let's have a look. What are the options you could do, right? Well, there's a very, very simple option. It's just turn down your production by X%, and then you emit X% less CO2, right? Except, okay, you've dropped your variable costs. You guys understand the difference between variable and fixed costs, right? So a variable cost is something that you pay per ton of product, whereas a fixed cost is things that aren't variable with the amount of product you make. That would be something like your salaries, or your insurance, or the capital you have to pay down on the loan you took to build the plant. So you can turn down the income and the variable cost, but you still have the fixed costs, and then very, very quickly you run out of business. Okay, so just turning down is not for many or for most an option. It's an option that will actually maximize your pain. So we're not going to look at that option, right? So what else can we do? Well, we can optimize our plants. You don't emit CO2 you didn't generate in the first place, right? So we don't waste steam, we don't waste heat. We recover pressure where we can. And this is great, but it's continuous improvement, right? This is the kind of thing technical support teams do on a continuous basis, every day, continuous optimization of the plants they're running. So for a research engineer, this is nice, but not that interesting. Okay, so we can capture and sequester or utilize the CO2, right? CCS, CCU, or big topics. Who's done that commercially? Just about no one. So now it's a new technology. It's not necessarily an in-house technology. It's something we're going to bring in, we're going to analyze, we're going to pull apart, we're going to do our economic evaluations on that, we're going to see what we see as the risks, work a bit deeper into that. Maybe we want to tweak the technology, maybe you want to use company X's, not company Y's. So this is becoming a bit more interesting, but it's a study, right? It's not necessarily going to be a tech development. You could say, okay, well, I can turn down the volume, but I want to maintain the profit. So I shift my entire products to products that have higher margins. Okay, now it's interesting. Now I need to develop new flow sheets and then to integrate these flow sheets with the existing units that I keep. Maybe I only keep utilities, but I still need to tie in with that. And you need to start developing new markets because you're not in these markets, otherwise you'd have these plants already. And to develop new markets, well, that's a marketing exercise, but marketing guys need something to market. And so very often you're going to have to be producing representative samples on pilot scale to start seeding the market, to start showing people, yeah, we've got these benefits over the existing products, etc. So this is starting to become real work for us now. Then we can say, okay, but we can also look at completely different energy sources. We don't have to burn coal or gas to generate our steam. Maybe we need nuclear power and we study that. Maybe we look at PV and wind, but that's variable power sources now, right? So now the question is, okay, I want to run my plant continuously 24/7. Do I store electricity? Do I store heat? Do I run my upfront units during the day and then make double the amount I need for the downstream units and store that, which is now the technology option and which is the economically attractive option. So that's becoming a lot more interesting now for a research engineer. I can also look for alternative feedstocks, right? So Sasol, you guys will know, runs off gas and coal, but maybe the feedstock of the future for us is wood chips from forestry waste or waste paper, or maybe we plant some specific fuel crops that we're going to harvest to generate diesel and petrol and jet fuel. Maybe we harvest algae, down at the coast, and we build a little plant in Durban to generate the oil, which we further process in a refinery. It's blank slate time, right? And this is now exactly where the day-to-day work for an industrial research engineer comes in, but also very much for academic research engineers, right? It's just the specific angle from which we're looking at this problem may be slightly different. So as you go down this list, much more interest for research engineers, whereas when you're at the top end of this, maybe it's more a plant support engineer's field of interest. And then somewhere in here, we're going to say, okay, this is what we're going to do. And then our design and project engineers come involved. Okay. And of course, everywhere here, it's techno-economics and it's risk assessments. Will it work? Will it work for us? Will it work in our process? Will it make money? And if the answers to all of those aren't yes, then you recycle. When you change something, you look at a different option. Okay. So this is, I think, broadly what we do. So I guess the next question is, who are we? Right? What type of people do we have here? Well, obviously, we have Megamind working here. Otherwise, it would be boring. So you do not have to have, I don't know, 170 IQ. You don't have to have a PhD. What you need, absolutely non-negotiable need, is technical curiosity. That is what sets apart people who thrive in this environment from people who absolutely hate it. If you're not curious 24/7, you are not going to enjoy working here. You must get excited by change. You must get excited by new problems, new technologies. If that frustrates you, that you constantly have to learn new things, then you need to go find yourself a different environment from industrial research. Okay. Postgrads are nice. I certainly would give you the benefit of, of your postgrad qualification when I interview, but it's not a requirement. So in our team of, I think we have about 45 engineers, but half the guys have masters, half the guys have PhDs, but there are also very successful engineers, and some of our best engineers who do not have postgrad. So what does a postgrad give you? Okay, well, a PhD gives you a field of specialization, but it's a narrower field, right? You know more and more about less and less. And if that field happens to coincide with something you're interested in, then that's a huge benefit. But if it doesn't matter. What does a master's give you? A master's degree, to me, as the guy interviewing you for a job, tells me that you have experience in tackling ill-defined, open-ended problems without significant support, which is fantastic because that is basically a job description. Yeah. So if I have to interview somebody who's just got a bachelor's versus somebody who's just got a master's, the guy with the master's is going to have a significantly better chance of landing the job. If I have to interview a guy just out of university with a master's versus a guy who spent 3 years working in tech support, it's a much more level playing field now, and the individual's skills and experience and how you interview is going to play a much bigger role. Right? If I'm looking for somebody with a very specific skill set, for example, maybe I'm looking for a guy with controls experience, and if you have a master's in that field, that's fantastic. If you have industrial experience in that field, that's fantastic. And if you have neither, the odds are probably against you. But generally what we're looking for are people who can pick up anything. I'd much rather have 2 generalists than 2 specialists, because the generalists can also become specialists, where the specialists tend to not to want to become generalists. Okay, so in short, postgrad is nice, but curiosity is much more important. And guys, coming from a guy who has conducted hundreds of interviews, postgrad and undergrad bursaries, and filled lots of positions, I'll give you this one piece of free advice if you're ever sitting in an interview. All things being equal, the person who brings the most energy into the room is most likely to walk out of the job. Right? So I know interviews are intimidating and you get nervous. Don't let that get hold of you. Be excited. Be happy to be there, even if you have to fake it. Just fake it properly. The guy who has the most energy, who seems the keenest to have the job, is, in all things being equal, the guy's going to walk out of the job. Okay. Right. I think I'm out of time, if I'm not well over time, and I'm open to any questions. So you guys can ask.
Thank you so much. Thank you so much, Braam, for that insightful talk. It was really interesting. I will hold on for questions a little bit later on during the Q&A session. So let's move on to the next talk in the meantime. Our next speaker is Dr. Tanya Hughes. She is the manager for capacity development in research and technology. And Tanya will be presenting an overview of the Sasol bursaries and the graduate development program. Tanya, thank you so much again, and over to you. Thank you again, Braam.
Thank you, Prof. Just let me know if you see my screen.
We can.
Okay, perfect. So I'm going to very quickly go through the first couple of slides, as they are more for general information, and Braam has already taken up most of our time, so he'll owe me a chocolate for this. So just a brief background. So my name is Dr. Tanya Hughes. I'm the Capacity Development Manager, as Prof David has said. So my background is I'm a scientist, so it's more the visuals that Braam showed of the lab coats and being in the lab is more relevant to the science side, and I can relate to that, as that is where I started, and I did a PhD in organic chemistry. So we do have multiple disciplines that report into our structure called RNI, RNT, RND, whatever you want to call it. But Sasol also employs, as Braam mentioned, all of these disciplines throughout of our process as well. So even though it's centralized and concentrated in a research environment, we have a lot of scientists and engineers working throughout all of our processes and even on the corporate side. So as you move and you define where you want to be, you can almost move around into the corporate side as well to dip your fingers in there and see if that is a more relevant space for you. So this is really just a background slide on Sasol for those of you that are not familiar with us. So we, as Braam already mentioned, we have multiple plants right around the world. We have about 33,000 employees, of which most of them are part of South Africa or South African based. If you saw all of the plants that Braam mentioned, we all want to go visit there, but probably if you put your hand up as an engineer or a scientist just coming in, you will probably end up at Uzbekistan or Nigeria, so be careful what you wish for. But there are very few, but there are opportunities to move around within the different units if you would like to do that at a later stage in your career. Again, just a little bit of an overview of what we do and where we are. I'm just going to skip through this. And also here, so we had a, Sasol has gone through multiple transitions and multiple movements into different arenas and different spaces within our technology areas, but we also have moved along with our academics as well. We always try to keep connection with our academics throughout the country. And we also like to partner and collaborate with those academics on a continuous basis. Little bit of an overview of how we conduct our university engagement, and we follow 3 different models. So one, you might have heard of, some of you, and if not, this is then your first introduction to it. We have a very vast postgraduate bursary scheme that we give bursaries to both masters and PhDs, as well as undergrad bursaries that I did not really mention here, but we also have a very big undergrad bursary scheme. But for an R&I or research and technology perspective, we focus a lot on our postgrads. So we have postgrads, masters, and PhDs in both our science and our engineering disciplines. And some of these postgrads are doing specific research that is of relevance to Sasol. Others, we just, as Braam said, had a memorable interview that we could feel the energy, we could feel the passion of that person. And even if they're doing a project that's not specifically related to any Sasol area, the passion and the willingness to learn and what they showed us in an interview becomes very, very important, as they then still would get a bursary, even though they don't do something directly related to what Sasol is doing. So then we also do contract research, and we also have a very big collaboration with the NRF at this point that some of the academics within UKZN and around the country is involved with, where Sasol defines themes and the researchers can then apply for grants. And we just launched the Young Academic Accelerator Program as well under this banner that is being reviewed currently. Okay, so this is just, again, high level of this collaboration. I'm not going to go through this again. This is just a view of our current bursary pool. So you would see that we spend around 40.7 million Rand on bursaries per year, which is a significant investment. So even though you might feel, but I don't have a bursary, I've been applying, continue to apply, because it is a significant investment for Sasol. It's how we feed our talent pool. It's how we feed our succession pool, and how we get the young engineers, as Braam now said, into the whole Sasol gears and dynamic, and train them and develop them to become the specialists and the generalists that Braam has spoken about. So if you are fortunate enough to become one of our bursaries, you will then be absorbed into our graduate development program, which is called Engineer in Training or Scientist in Training, and you will go through multiple development stages within your first 3 years of your career at Sasol. So this is again a very high level overview of our graduate development program that is done for both our scientists and our engineers. Rotation means you get experience and exposure within different areas within Sasol. So for example, in Braam space, and then also on the plant, so specifically plant-based experience, as well as in some of our more corporate or business areas as well. So this provides you with the unique opportunity to develop a unique skill set that can then be used in any of the areas that you've been exposed to, and be ultimately appointed in one of those areas after the completion of this program. So a little bit on our bursaries. So unfortunately, Sasol has not opened up a call for new bursary applications for 2025, but please be on the lookout for any of these opportunities that will open up in 2025 for possible bursary opportunities for 2026, if that makes any sense. We typically look or focus on the engineering disciplines, chemical, civil, as well as electric and industrial engineering, mechanical, a little bit, and also a little bit in the metallurgy and mining engineering. Mining is also a very big portfolio. We actually did open a call for the mining side this year, as that pipeline needs to be continuously filled, as it's a very, very important part of our business. So what do you call it? Chain. Okay. Then we do on the science side, we focus on chemistry, geology, as well as data science. And for the science side, though, an honours is the minimum degree that is compulsory to do with a Sasol bursary, but you will not be appointed into a research capacity for Sasol if you do not have a postgraduate degree, such as a master's or an MSc. So on the engineering side, it is a wish. On the science side, it is mandatory for a research position to have an MSc, minimum an MSc or a PhD. Then we also look at our BEng technology on the University of Technology side and the mine surveying. So please go and look at that link that I've posted there. I'll post it in the chat as well. So sasolbursaries.com, and you will have all of the up-to-date information around our bursaries, how you apply, when you apply, and when calls open. Then typically, as Braam already mentioned, a starting career at Sasol with any of those qualifications would then involve you to become either a process engineer, a project manager, an R&T engineer, as already mentioned, a process scientist or an R&T scientist, data scientist, and as I've already mentioned, a lot of our scientists and engineers even move into spaces that you would not typically find a scientist or an engineer in the corporate side, in the business development side. In all of those areas, our scientists and engineers make a valuable contribution. So I now speed talked through my presentation. So if there is any questions, we will answer that afterwards. Thank you so much.
Thank you so much, Tanya. That was also quite insightful and of definite interest to the students. I'm going to move on now to the Q&A session. Just remind me about this one. So the students can put their hands up and they have the right to be unmuted, and they can pose questions directly to our speakers. And then also there's been some questions that have been posed in the chat bot. So we can select from there, and then the speakers may answer those as well. So do the students now have the opportunity to put their hands up and ask some questions? And then Shansla, can you just confirm for me? Okay, I'm just going to monitor from my side then. There we go. We can see a couple of hands coming up. I've got a hand from Miss Mhlongo Bongo Kwake. Can you unmute and come in with your question?
Go ahead.
Go ahead with your question, please. I think you're unmuted at the moment.
Maybe while we wait, I see there's a question in the chat about external applicants.
Yeah.
I think the short answer is yes, but Tanya can elaborate.
So
Okay.
I was busy typing as well. So we do take external applicants for our graduate program, but in saying that, yes, it is only when there are insufficient number of graduates that finished, and we need to top up the amount of engineers or scientists we require within the company. So for example, if we have 40 engineers that's part of the bursary pool that is graduating, but we need 60, then we go out on a call to top up that 40 with an additional 20 with external applicants. You just have to make sure you always keep your eye. So follow Sasol on all of our social media platforms, such as LinkedIn, Twitter. I think we're on Twitter. I think we're on, oh, it's now called X, sorry. I am definitely a Gen X as well. And then we are also on TikTok and Facebook. So follow us on any or all of those social media platforms, because all of that information is continuously placed on those platforms. So if there's ever an external call, you will find it there.
If you're old like me, then you go look at sasolcareers.com.
Yes, or that, yes.
Okay. Okay, thank you so much, Tanya. And, are there any other questions from the attendees? You can put them into the chat as well if you're a little bit shy and don't want to speak up.
If you want to make a proposal for what chocolate I owe Tanya for taking all of her time, you can also put that in the chat.
Okay, there we go.
Yes. I'm assuming that question on electives based on green technology, green energy. Yes, I think you'll find when we advertise for postgrad bursaries, that's usually we give fields we're interested in, and sustainable technologies is definitely going to be on the list. Right, so Sasol definitely has committed to 30% greenhouse gas reduction by 2030 and net zero by 2050. I think we have a vague idea of how we're going to manage this for 2050. I can give you an absolute guarantee that the technologies required to get to 2050 haven't been invented yet. We need people to get us there.
And I can also add to that is that so when we do open the call for applications for bursaries, we do have certain themes under which those bursaries fall. So for example, if we see that there's a gap within Sasol with regards to green energies and green technology, we would go on a specific call for students that have had that as electives and that will be doing projects based on those themes. So the same with our NRF initiatives, you will see that all of that is geared towards, the just energy transition and greenhouse gases and green hydrogen and all of that. So all of those themes are then themes that Sasol specifically relate to, even though we don't really influence the type of projects that you do. On the next question, computer engineering is funded, but to a lesser extent. We don't have the bulk or the concentration of computer engineers that an IT company would, for example, have. So even though we do fund them, it's to a very, very little extent, and that is more from an undergrad perspective, not a postgrad.
There's also, if you're into data science, there's also a limited number of bursaries available for data science, data engineering, I think.
So Zipile, I see your question. We have not, I don't think, Braam, we've ever taken students with information systems and technology.
I can't recall, no.
No. So unfortunately, up to date, no. It is something we can maybe look into, but I mean, we are a science and engineering company, very much an engineering company. So our focus on bursaries is for those disciplines. But it's definitely something I can get information of for you. Okay.
On the VACWork one, it's a tougher one. Taking in VACWork students is actually quite a commitment from the manager's side, because it's in December, right? That's the first thing. I've always said, yes, we must do this in the June holidays, but we somehow never manage that. And December is also when my guys go on leave. So I have to make commitments to people being here. We must find projects. So the bursary office insists that we first take, whoever's willing to take VACWork students, first take our in-house guys. But we have certainly taken out external students as well. I'm not sure whether that's just through the Enzalo Foundation or general applications, but it's managed by the bursary office.
Yes. So yes, Braam's completely right. So we do take external, but it is, like Braam said, first preference is given to our bursary students. And it is quite a huge undertaking to get VACWork students into Sasol, because with our bursary students, they are already contractually obliged to, fit into the confidentiality and ensure that they are aligned with everything that Sasol requires. So taking external backwork students are a little bit of a more complex undertaking. But again, those types of calls will be on the bursary website or will be issued on the social media platforms if we do find ourselves in a year where we can actually take on external backwork students. So data science without honors or postgrad degree, I am not sure, Braam, if you have information on that. I don't think so.
The data science team, I think, is officially called the Industrial Statistics and Machine Learning.
Yes.
So those guys tend to have masters or PhDs in statistics. I don't know that they would necessarily easily take somebody who does not have at least an honors degree in there.
So
Although
what I'm going to ask, is Prof, if we can get a list of these questions that we don't have the exact answer to, then I can definitely, get that frequently asked questions and get answers for you on these that we are not specifically 100%, sure of. Then I can send those answers to you and you can forward it to the students.
Maybe just tangentially to that one, just quickly, there's been a drive for a number of years in Sasol now to get our engineers more involved in data science, right? The dream is one engineer day job, fly-by-night data scientist guy in every plant. To the point where we have worked with University of Stellenbosch, where they're now doing a taught masters in chemical engineering on data science specifically, and Sasol is committed to sending, I think, 50 people there or something. But if you're interested in data science, you do not have to have a degree in data science to come and work here doing data science. And to be honest, I think you're going to do better by being an engineer that does data science than being a data scientist who tries to do engineering. Okay.
Then, so the currently most relevant topic within process engineering, Braam, you can answer that, is all things green.
My whole team has been working on nothing but biomass for, I swear, the last year. So yeah, no, sustainability is yesterday, today, and tomorrow for us at the moment. Yeah, absolutely.
And so how often do we prioritize BSc chemistry students for bursaries? So unfortunately, our pipeline for our science is a little bit smaller than the pipeline for our engineers, because Sasol is overall an engineering company with a small contingent of sciences that support that. So the number of scientists that we have bursaries with or bursaries for are less, but we do give bursaries to scientists, to BSc chemistry students often. You just have to make sure you apply, and you apply. So the number might be less, but we do that continuously as well.
Tanya,
yes.
In the interest of time, can I maybe just say that maybe we take one or two more questions from the chat? And then I'll also just encourage the students that are on the line, if they've got a technical question for Braam, then they can put their hand up and they can ask that as well. We're really looking forward to something from there. But yeah, maybe just one or two more questions from the chat. Just
so I think,
to round
Braam,
up.
you can take Salvation's question.
Yeah, ChemEng postgrad on a ChemEng topic, but specialized in machine learning, absolutely. Then I can probably make room for you in my team. So I've got Fabian in my team that is masters in fault finding, so machine learning techniques. We're building, all kinds of data science and machine learning things. It's part of advanced process modeling, right? Fundamental modeling is always going to be the first thing you try, but you get to a point where fundamental modeling simply cannot take you to where you need to be, and then there is a data-based approach is always there. Be very careful by just pulling that tool out of the box first. Data-based modeling requires good data, and plant data is notoriously iffy, right? So we spend a lot of time massaging data, cleaning up data, doing fancy reconciliations on data, and only then can you feed it in. And for the biggest machine learning project we kicked off, what we spent the last 3 years doing is fixing instrumentation on the plant we need the model for. Okay, so yes, machine learning is awesome, but machine learning in real life has some issues you need to deal with first. And that's usually data quality.
Okay. Thanks so much, Braam. That was an excellent answer to that one.
I can also answer the question, are there any sustainability related jobs that engineers working at Sasol? Absolutely. It's all of the jobs.
Yeah, all of them. All of them. We all want to sustain our salary, so please come and help us.
And it's like Braam said, you're a generalist. And if you're a generalist, you're able to work anywhere within Sasol. Where we put you, you'll be able to become a specialist for that area and then move again to a new area where you would become the specialist.
We've been joking the last couple of months that the requirement to join my team is a tractor license. Maybe it should be a combine harvester one at this point.
Tanya and Braam, thank you so much again for joining us for the Tech Talk this afternoon. Your presence here was greatly appreciated. So much for the insights. I'm sure the students enjoyed that as well. They're going to follow up. I'm sure you're going to get a lot more followers on your social pages going forward. And yeah, they're going to take every opportunity to join you in your engineering endeavors. I just want to remind the students that we've got another TikTok coming up on the 21st of August by a company called Intellect. So please just make note of that. The invitation will go out quite shortly, and make sure to register for that one as well. From my side, I just want to also thank the technical team behind the setting up of this program. And I want to wish you all, a safe and interesting further day. Thank you so much.
Thank you guys for the opportunity. Thank you. Bye-bye.
Great to talk to you. Bye.